Okay, so we've talked about tuples in general and how they might be represented in various different ways. Let's have a look at how Postgres does it. If you want to find out all the details of the tuple structures, you can look in the include subdirectory of the source code. And if you want to have a look at the functions, you look in the backend access, common. And then under that, there's a whole lot of tuple-related functions. One very important one, heap form tuple, that essentially corresponds to what I call MK tuple, make tuple, in one of the other videos. It has a number of pieces of information, so it's got a descriptor which tells you information about all of the different attributes. So you know how large each attribute is, what type it has, and so on. You've also got an array of actual values which you're going to use to build the tuple. And also, interestingly, and we'll see this in a couple of other places, you need an array of effectively booleans to tell you which of the attributes are null. So we don't have a value that we can use to represent null. What we have are separate arrays with flags, and each flag says this attribute is not null, this attribute is null, this attribute is not null, not null, not null. When I say this attribute is null, I mean attribute value for a particular tuple. And also, obviously, you want to clean up tuples once you've finished with them. So you can feed in the same collection of information, and that will remove the tuples. All right, so what do Postgres tuples actually look like? They're a contiguous chunk of memory sitting in a buffer. So essentially a record. The record has some structure, of course, obviously it's got the different attribute values, but it's also got a header whose details we'll see in a couple of slides' time. So we've got the header and then some data values. And data values in Postgres are represented by things called datums, individual data items, I guess. All right, so what's a heap tuple? A heap tuple, and we're going to see this a fair bit in Postgres, that we're going to have a structure which contains data, and then the way we access that structure is via a type, which is a pointer to an instance of that structure. So a heap tuple is simply a pointer to one of these things, which contains the length information, so that's the total number of bytes in the tuple as it's stored in the buffer. Self-item pointer, no idea. OID, this is important because we need to know which table the tuple came from, because with that information we can get all the details of the schema, for example. And a heap tuple header, which we'll have a look at in a minute. No, in fact, we'll have a look at it right now, because all it is a pointer to a location in a buffer, which is where all the actual, the sequence of bytes that represents the tuple is located. So there's a diagram that represents that. Heap tuple is a pointer to one of these heap tuple data objects. It's got length, basically that is the total length of this record in here, which consists of a header plus the actual attribute values. The self pointer, table OID, so we can refer to the table in the catalog, and the actual pointer into the buffer. Alright, so a tuple has a header plus data. What does the header look like? Well, once again, we've got this pair of type definitions, a structure holding data, and another type which is a pointer to one of these structures. All right, inside the header structure, a heap tuple header. Oh, and I should have said, why is it called a heap tuple? Because in Postgres, sort of regular data files, the pages in them, well, in fact, the file is called a heap file, simply because it just consists of a sequence of pages containing tuples or records, as distinct from index files which contain index tuples. We'll talk about them later. So heap tuples are basically just regular tuples, if you like. All right, so what have we got in here? We've got another data type. So we've got data types nested within data types, nested within data types. Because we're doing MVCC, there may be different versions of a tuple, and the versions can actually be linked together. So if a tuple is, say, updated, the old version of the tuple hangs around and can be viewed by appropriate transactions, but the new version also exists, and this CTID is a link between the two versions. Then we've got a couple of masks, which basically is a bunch of flags. For example, does the tuple have any null values? If it does, then we need some additional information. If it doesn't, then we don't need that information. And then we've got a pointer to the actual data, or rather this tells you how large the header is, and gives you the offset of where the data actually starts in the tuple. And then we got this bitmap, which tells us where the nulls are. I talked about not having a value called null, but having a bit that says, all right, this particular attribute is null. And here's what one of these tuple-headed data looks like. So we got the heap tuple fields. That was the first field of the heap tuple header data. And it contains this information that talks about who created the tuple, who deleted the tuple, if it has been deleted, and the command. So a transaction consists of a number of commands, and the particular command that did the deletion is stored in here, and then a reference to a newer version of a tuple. All of this information is required, well, maybe not that one, but these first three certainly are required to determine visibility of tuples under MVCC. Then we've got these flags, then we've got the offset to the start of data values. Basically what that tells you is what's the offset of this relative to the start of the tuple, and then we've got the bitmap. All right, so that's what a heap tuple header looks like. And some of the examples of the kind of things that are in the info mask. Does the tuple have null attributes? And here we're talking about a particular tuple. It's not, can tuples of this type have a null? This particular tuple has a null value for this particular attribute. Does it have variable width data values in it? Therefore, is it a flexible size tuple? Does it have external data? So does it have toasted stuff? And does it have an OID? In the past, all Postgres objects used to have an OID, and they included every individual tuple. At some point, people realised we're not using the object ID for regular tuples, so should we have them or not? And the default nowadays is not to have them. The only place where they're, I guess, mandated is in the catalogue table. Okay, so this thing tells us whether the tuple has nulls and where they are, which attributes they are. We can work out from this t-bits array. Right, so here are the the fields that are right at the start of the heap tuple header, the inserting transaction, the deleting transaction, and then we've got a field which has two purposes. It's either telling us where the command, or which command was the one that did the insertion or deletion, and then or, and that's why we're using a C union. So basically what that's saying is T field 3 could either be interpreted as a command ID or it could be interpreted as a transaction ID for the I guess the vacuum transaction that eventually removed the tuple. All right. So OIDs don't have to be in the tuple. If they are in the tuple, they're stored directly after the tuple header. Both of xmin and xmax are stored. Of course, if the tuple hasn't been deleted, then this will have a null value, or a value that doesn't represent any transaction. Value like 0 might be appropriate. And then you might say, why do we need both of these? You know, we could use a union, say, well, we've either got the inserting transaction or the deleting transaction, but in fact, we need them both to work out, once again, to work out visibility. If you like, you can think of these as specifying a duration during which the tuple is visible. That's not quite accurate, but it's a reasonable approximation. All right, now we've said that we've got a whole lot of data values. We've got to interpret those data values, and so we need some information that's a little bit related to the schema to do that. So how many attributes are in the tuple? And that would, I guess, include null attribute. Where's the tuple type defined? And that's defined in one of the catalogue tables. In fact, I'm pretty sure it's defined in PG_class. Is there any modifier for the type? Does the tuple have an OID attribute? Off the top of my head, I'm not sure what reference count is used for. And then we've got constraints. So basically this is an array of constraints, that's stored externally to this tuple descriptor, or to this struct tuple. On the other hand, we've got all of the information about the individual attributes is stored as an array following these fields. So this is yet another one of these variable sized arrays, where the size is determined when you actually create the struct tuple desk. You specify how many bytes you want, and that will determine how long this array is. Or you can look at it the other way. You know how long that array is, and then you malloc the appropriate number of bytes. All right, so yeah, we looked here, and finally we work our way down through layers of data structure. This tells us the details of an attribute, which table it comes from, what it's called, clearly important, what its type is. So you can see that there's a little bit of redundancy. Well, it's not actually redundancy. The type ID that we had here is referring to the type for the whole tuple, which, as I said, is stored in PG class. This will actually be a pointer to PG type. How long is the attribute? Clearly that's important. How many dimensions? If it's an array, you can see that the fact that we're allowing a 32-bit integer means that we could have quite a few dimensions. can the attribute be null, or is it guaranteed to be not null? Plus a whole bunch of other fields that I haven't shown here. One thing you might notice about this, the attribute length is defined by a 16-bit integer. That's a pretty big attribute value, and it's bigger than could be stored in a Postgres page. So you might wonder why they're using 16 bits, but I guess they're wasting a bit of space. I can't remember, is it 2 to the 12? That's 8K. So if they only require 12 bits, let's say that for the sake of argument, then they're wasting 4 bits of the attribute length value. Alright, so what about the attribute values themselves? They're all packaged up as things called datum. And what a datum is, well, it's basically just an integer. It's defined to be a pointer, but it's a value that could actually contain the real attribute value. So for an integer, the datum would actually hold the integer value. So if we're talking about, a value 42, then the value in the datum will be 42. It could contain a header, which tells you how long the real value is for var-len attributes. And if you think about that exercise where we had to subtract 4 to work out the length of the size of varchar attributes, or char10, that's because we have a 4-byte header at the start to tell how long the actual attribute value is. And also a datum may tell you that the actual value isn't here, it's in a toast file, and you'll have to go fetch it. Alright, of course, it's all very nice to know that we've got individual datums, but what we're interested in eventually is getting attribute values. And we showed some functions in the previous Tuple video where we could extract values of individual attributes, and that we had things like get int attribute, and we have a tuple and an attribute number. Alright, so heap get attribute contains a reference to the heap tuple. It contains an attribute number, so how many attributes there are, a counter of the number of attributes. Contains tuple descriptors, which give information about the individual attributes, and tells you whether the attribute is null or not. So this can't be part of the value. Attribute numbers can be negative to deal with special attributes like OID. So OID is actually attribute -1. If you want to find out more details about these data structures, then you can have a look in there. And finally, of course, we need to get the values out, and there's a whole bunch of macros a lot of the time. There may be some functions, but given an attribute, extract the actual real value contained in that attribute. So if we got a Boolean attribute, we take the value of that, which could be 0 or non-zero, and we do a check, is it 0 or non-zero? We cast that to a bool type in C, and then that's the value that we give to our C program that's playing around with the data. And there's a whole bunch of these things for extracting information and for going in the other direction, for taking a Boolean value and converting it into a datum, if you like. Alright, so that's how Postgres represents tuples. It's fairly complicated, but there's a top level thing that just tells you how large the tuple is in terms of total length of stored data, which is eventually going to be in a memory buffer. Then that contains a header and the actual data as a sequence of bytes, and then additional information that allows us to work out what type of data we're actually looking at, so tuple desk, things like that. And then, of course, we want to interpret the stored values, and we have to package them up as datum. Okay, so that's PostgreSQL tuple.